Thank you for joining our webinar today. Today we'll be talking about the challenges of detecting hydrogen gas. And this works. There we go. A couple of housekeeping rules just before we start the webinar properly. Please mute your microphones. If you've got any questions at all, please feel free to post them in the chat and they'll all be answered at the end. We'll save some time at the end for that. And just to let you all know, the webinar will be recorded today. So if you do ever want to rewatch the webinar, it will be on our company webpage and you can always have a look through again. So I should introduce myself. My name is Hamid Mahmood. I'm a business development executive here at Crocon. Been with the company for just under a year now. I've worked a lot alongside Paul, who will introduce himself in a second. We've been focusing a lot on hydrogen projects and the global scale and global market of hydrogen. Paul, if you want to introduce yourself.
Hello, I'm Paul Basham. I'm here as our company's principal scientist, and I've been at Crocon for 26 years now and developed many of our products.
Yep. So to begin this webinar, I'll give you a brief background and intro on hydrogen in general. And I'll start with the different types of hydrogen, right? So there are three types of hydrogen. The first is grey hydrogen. It's the most common form of hydrogen production, and it works by something called steam methane reforming. Steam methane reforming, in a brief description, is when you react methane and steam using a catalyst, and that produces hydrogen. It also produces carbon monoxide and carbon dioxide as byproducts, and is not a green source of energy because it produces and releases those and emits those into the atmosphere. Blue hydrogen uses a similar steam methane reforming process. However, the carbon that's emitted gets captured and stored underground. So some like to call blue hydrogen as carbon neutral because it's not emitting that carbon, instead it's storing it. However, a lot of political and government shift and media focuses on green hydrogen, which is the third type. Green hydrogen is actually a renewable green source of energy, and it's produced by electrolysis, which is usually powered by renewable electricity. An example of that would be hydroelectric dams that you see sort of across the globe nowadays. And yeah, a lot of the focus will be on green hydrogen, I believe, in the future. Brief introduction to hydrogen. There's a collective global effort to reduce carbon emissions by 2050 to decarbonize our fuel supply. One way to do that is to use hydrogen. Hydrogen, when burnt, produces water vapor as a emission. Water vapor is net neutral, so it acts as a green energy source compared to other sources such as fossil fuels. No GHG release. An example of where you could use hydrogen instead of another byproduct, another non-renewable energy source, is using hydrogen in place of methane. So for the UK, for example, methane gas we use methane gas in our natural grids and pipelines, and if you replace that with hydrogen, the methane that's used actually, when burnt, produces carbon dioxide. The hydrogen will produce water. A brief description on sort of global timeline and what the predictors are of sort of hydrogen markets, essentially. So in 2016, Paris Climate Agreement came together. Global governments came together and suggested that we need to put a stamp on carbon emissions and the global rising of temperatures and whatnot. And one of the promises was actually to cap and keep well below 2 degrees Celsius for rising global temperatures. And this was reiterated at the COP22 and COP26 events, where again there was actually a more specific focus now on hydrogen as a renewable energy source. And so a lot of countries actually agreed to invest and develop technology and understanding in hydrogen production and hydrogen generation. And on this timeline, as you can see, you have various examples of countries that have developed their own green hydrogen plans or hydrogen plans, all within the next 5 to 10 years space. And I think to date, about 40 countries have actually developed their own hydrogen roadmaps. Alongside those, there's already been forefronting hydrogen projects such as transport projects or generation projects that have been becoming more and more common across the globe as an energy resource. Alongside that increased global effort, there's also been increased regulations and legislations regarding hydrogen generation. And this ISO 22734 is an example of that. So this regulation actually states the significance of having reliable fixed gas detector systems at hydroelectric dams and water electrolysis generation systems. And this is just one example. There are plenty of other examples of regulations that are required in the hydrogen industry, and there will be many more to come in the future, I'm sure. It should be noted, however, that most countries do tend to, for the moment, work within their own legal guidelines when it comes to transport hydrogen or generation. Whatever they sort of have in those industries already is what's being used, but there will be a shift, I believe, towards hydrogen-specific requirements. I'll pass you over to Paul now to talk about the dangers of hydrogen.
Hello. The hydrogen dangers divide down into a few categories. One of those is its flammability. It's very highly volatile and flammable substance, a very mobile gas, and when its concentration exceeds 4% in air, it can explode. It's got a very fast flame front, so there's a fair amount of force behind it as well, and that happens when you get fuel and air and a spark present at the same time. You can have that problem. Its reactivity and flammability mean we have to look after it when we're generating it, storing it, transporting it around, and using it. It's not itself toxic, but when it accumulates in enclosed spaces, it can, of course, displace the air, and the air contains the oxygen we need for normal life, and so you can asphyxiate, in theory, if you have too much hydrogen present. However, what you usually find in practice is that hydrogen is such a mobile gas that it tends to escape from enclosed volumes, and so it tends not to build up quite so much as other asphyxiant gases. Perhaps carbon dioxide, for example, that collects in because it's 1.5 times the weight of air, and displaces the air in the same way, but doesn't disperse very quickly, and so it's far more of a danger. Hydrogen is, though, a colourless, odourless gas, and certainly if you're in an enclosed space, it can fill a volume from the ceiling downwards, and when it gets to head height, you'll be breathing that rather than the air you wish. Okay. What are the challenges? It's a small molecule, as we said, very mobile, and so it will find any leaks in any pipe that it's passing through or any container you store it in. It can sometimes pass through the walls of the container if they're not perfectly formed. It also causes its own problems. Hydrogen in a metal container causes a sort of hydrogen hardening of the metal, whereby the hydrogen goes into the surface of the metal and can weaken it, and then changes in temperature or knocks can cause it to crack far more easily than it otherwise would, because it's nowhere near as ductile as it was. Any small cracks that form like that or through any other means, and the hydrogen will find them and will escape compared with any other gas which is far less mobile. As an indication of how mobile hydrogen is, it's the speed of sound in hydrogen is just over 1,300 meters per second, whereas for normal air it's around 330. So you can see just how much more mobile the speed of sound is, and the hydrogen molecules. That also transfers into how fast flame fronts are in hydrogen. You know, the characteristic pop you get when you explode a test tube of hydrogen. That's due to the mobility of the flame front, and it causes a problem in its own right, which is you're not going to put a hydrogen fire out very quickly, because it typically goes on until it runs out of fuel. And that's also true if you've got hydrogen mixed in with other fuels. The hydrogen carries the flame front to other unburnt gases and solvents, and continues the fire, making it harder to put out.
Yeah, so there's an importance in the technology used for detecting hydrogen, right? As Paul just mentioned, some of the challenges that you face, especially to do with the molecular speed of the hydrogen molecules and whatnot. Here at Crowcon, we have a range of products that actually detect hydrogen at different levels. So, for example, we have pourables, fixed, and other ranges of products. I'm sure some of you might have heard of some of these. Initially, our product range actually uses ballistas, which I think Paul will talk about in a moment. And these ballistas actually detects percentage LEL for hydrogen. But alongside the ballista technology, we also have other technology with some of our newer range of products, such as the T4X, Gasman MPS, XGuard Bright, which actually detect hydrogen as one of up to 19 gases for a single sensor type. And I believe Paul will actually talk about this technology just now.
Okay, you can see here on the slide, top right, you can see the images of the MPS sensor. It's a standard size sensor that we have in a growing number of our products now, portables and fixed. It's based around the principle of molecular property spectrometers. I'll describe how that works. But first, hydrogen is traditionally detected in all concentrations using thermal conductivity, and thermal conductivity is a very good way of detecting hydrogen because it's such a mobile gas. It can take heat and transport that away from the sensing elements very fast compared with other gases. Makes it highly distinct, and the signals you get show it to be hydrogen reliably. So the MPS sensor is like a super accurate version of a thermal conductivity sensor. How it works is you have a ceramic disc in there about the diameter of a human hair, so very light and small, and that is ramped in temperature from room temperature up to 1,000 degrees C and back to room temperature every 2 seconds. What happens then is we can plot the thermal conductivity versus that temperature, and we can look for kinks in the curve that we get, and those will be at characteristic points, a sort of fingerprint for the gas we're looking at, or the gases we're looking at, and you can look at the gradients either side of those characteristic points and determine just how much of each of those gases are present. So firstly, we can tell what gases are present, and secondly, we can tell how much of each of them are present by comparing with some lookup tables in the microprocessor, which is inside the sensor. So in that way, we can then add all of those component concentrations together and give a true % LEL output, regardless of gas mix type. Now we've got 19 gases in those lookup tables, but there are some general formulae as well, which are reserved for gases of certain weights, and so we can actually detect more than those 19, and we're adding to that list all of the time, of course.
Yeah, so there is also an MPS video on our website, which you can always watch if you want to learn a bit more about it or want to have a refresher. We have a couple more technologies to talk about before we can go through some questions. So if anyone has any more, feel free to drop some in.
The Plista, which Hamad will run the video of as I'm talking, is basically a small flammable gas sensor. It's a metal case with a sensor on the front. Internal to that, there are a couple of beads. These are concrete beads, and impregnated into that surface on one of them is a catalyst, and on the reference bead there's either a poison catalyst or no catalyst. And internal to those beads there is a thermistor, and so we put energy in, heating those up to about 230 degrees, and the catalyst takes the reduces the ignition temperature of, let's say, a methane and air mixture down to that temperature, and we look at one against the other, the active catalyst bead versus the reference bead, and we look at the resistances. We compare those resistances, and by so doing we can tell how much gas is present due to the temperature rise of one bead over the other. Electrochemical sensors. These are small cans of plastic cans, usually containing electrolyte and electrodes. These electrodes are usually precious metals, and although there's tiny amounts of them, and we can choose the electrolyte type and the metal of the electrode to detect various toxic gases. We also can detect oxygen using this method. What you have in each case is an enclosed plastic can, and in the front of that there is a small capillary. Gas gets down that capillary from the outside to the inside, and hits the working electrode where it is immediately detected. If you're detecting hydrogen, for example, then you have one concentration of hydrogen outside, you get a certain amount of gas getting down the capillary and being detected by the working electrode. If you have twice the concentration outside, you get twice the transport rate through that working electrode, down to the working electrode through the capillary. And so you can see by looking at the electrode signal exactly how much gas there is outside the sensor, and that's how it works. We've got two ranges that we work over for electrochemical sensors, not just the 0 to 100% LEL as before, or 0 to 4% in air in this case, but also other forms of electrochemical sensor that can measure 0 to 2000 ppm, so far more sensitive for leak detection purposes. And we provide both, of course. That's that.
Perfect. Well, thank you everyone for joining in on our webinar about the challenges of detecting hydrogen today. If you do want to find out any more, please feel free to check out our website. We have various different white papers and blogs about hydrogen or different hydrogen use cases. We also have an industry page about hydrogen itself. If you want anything more personal, feel free to reach out to marketing@crowcon.com, where we can pick up any answers or queries specifically there. Don't see any questions in the chat at the moment, so feel free. I'll give it a couple of seconds to see if anyone's going to pop anything in. Again, yeah, feel free to check out any of our resources in your own time. Okay, I guess there's no questions today, but that's fine. All right. Thank you, everyone. Thank you, Paul, for joining me.
Welcome.
And have a good day.
Thank you.